Okay. I feel a bit confused to bring you back to very mundane things after this morning of dealing with our universe. And okay, this is not going to be very high level speculation, just more kind of a grassroots or bottom-up talk, going back through concepts which are certainly familiar, but maybe seen in a slightly different light. At least for me, it was a different light at some moment. And the interaction we didn't expect, well, no suspense. This, of course, refers to the scalar bosons. And the time refers to 1970s, where before this all standard model thing started. I'm not going to do history. I'm just going to mention a few things. Of course, in between, there was this happening. And we start with the familiar picture of Robert Brout. In July 2012, kind of the last piece, or possibly the last piece in the standard model, fell down. And we now have confirmation of what was guessed for a long time. But having the confirmation means we have to come back and think a bit further. This is, of course, the outcome, which is the Nobel ice cream, which has, I think that's what people are going for. Okay. Now, once upon a time, I will not try to give you my birth date. Once upon a time, we had 3 or 4 types of interactions. And it was well known, the electromagnetic, the weak, the strong, and the gravitation. And when I was a student, I was asking myself a naive question, which was, how do you tell when interaction stops being strong and becomes getting weak, or vice versa? And of course, it was a stupid question, but I didn't get the answer at the time. And of course, the answer is that, well, there are 10 orders of magnitude at that time between strong and weak interactions. So there is a big gap of 10 orders of magnitude. So, I mean, there is nothing in between. And that was clear. Well, nowadays, I think this is not clear. Well, these are the 10 orders of magnitude. This is the answer I should have gotten. Well, I've put new numbers here, like the tau lepton, which was not known at the time. But you see, for example, that the lifetime of a particle of 1.8 GeV, the pi, resonance, is 10 to the minus 24 seconds. For a lepton, it's 10 to the minus 13 seconds. And you have indeed those 10 or 11 orders of magnitude there. And that should have been the answer at that time. And complemented with the fact that if you do a just order of magnitude calculation, assuming strong coupling 1, well, you get 10 to the minus 25 seconds, which means that the first one is in line with what you expect, and the other one is 10, 11 orders of magnitudes weaker in its decay. Longer lifetime, weaker decay rate. Good. So it's difficult to explain. Then there are some other numbers, like the neutron and the muon lifetimes, which were known, not to this precision, and the proton, which is just there as a joke. Now, very quickly, it became clear that you could explain all those numbers with one simple hypothesis, which was that in between here, the process, the decay process, whichever of those decay process, tau, neutron, or muon, would go through a heavy particle, let's call it the W, and then you can work out the lifetime by this formula with the mass of the W there and the coupling G. Of course, you have 2 parameters. You can fit those parameters as you like, and for any decay rate, well, you have a choice between weak coupling and large mass, whichever. Well, it so happens that you can just work it out. There is only one combination which works, which is to give m over the order of 100 GeV and g of the order of the electric charge. Actually, g is of order 1 in this game. And indeed, once you have done that, you get all those 3 lifetimes, sorry, this is a bit shifted. I mean, the muon lifetime, all those 3 lifetimes fall into line, which means that there are no weak interactions. because, okay, mean G is of order 1. There is no weak interaction in this thing. There is just a heavy intermediary. And therefore, the name weak interaction is a complete usurpation in this way. We have now unified, well, we could have guessed, but now we know that we have unified interactions. So I think we have no weak interactions. No weak coupling is appearing in the theory. This is well known. This is just restating it. OK. What does that mean? Should we abandon completely the notion of weak interactions as being separate from the others? And, well, actually, when I was asking myself that question, where's the difference between strong and weak, there was another answer, which is, yeah, but the weak interactions are characterized not so much by their flimsy strength, but by the fact that they violate about everything which can be violated. For example, the big surprise was parity violation, and that came as a surprise to all theorists. And then they scrambled to write it. Well, they knew, actually, that you had two inequivalent representations of the Lorentz group for fermions, and they could have put in P violation from the start. Simply working with electromagnetism, QED, and still the way we are teaching QED in the courses, we are putting people on the idea of parity conservation. When I teach QFT, quantum field theory, I avoid starting with electromagnetism. I start with the chiral theory, because I think this is the proper case in 3+1 dimensions. The CP violation, once the P violation was known, the CP violation was actually predicted by Levo-Kuhn, and it was searched for. So that was not a surprise for theorists. Once they had digested the first one, they got it. OK, so would that be a way to characterize the weak interactions as the interactions violating P or violating CP? Now, for P, actually, no. Because for P, you don't need anything specific. Any gauge theory in 3D is linking left-handed particles to left-handed particles, right-handed particles to right-handed particles, and it's just sufficient to put different G, L, and G right there. You don't need anything specific. So a pure gauge theory will do it without any problem. So actually, the expectation, as I mentioned, and I think this is the way we should teach it, the expectation is that you have parity violation because we are dealing with gauge interactions. Actually, we knew this, one couple of comments. This means that parity violation has absolutely nothing to do with the absence of presence of the right-handed neutrino, as you can still find in some textbooks. You have parity violation in purely hadronic systems, and actually parity violation started from k into 2 pi and k into 3 pi. This was known. Okay. So actually, the question is, the surprise is that we have parity for long-range forces. And for long-range forces, I would like to include also the strong interactions, SU3, which, okay, on GeV scale, this is long range for me for the moment, okay? But you know what I mean, because there is no symmetry breaking. And so is it an accident that we have parity? Because for us, parity is such a granted thing. Okay, there are a few left-handed people, right-handed people, but our feeling is that parity is respected, and it's certainly respected for all long-range interactions. So is it an accident? Well, let's try to think of starting with a grand unified theory, like SU5, SO10, if you prefer. Of course, when you write a multiplet for a grand unified theory, you put all the particles to be left-handed or right-handed if you choose, because all the particles in one multiplet must have the same helicity. So you start with a theory with a 5 bar and a 10 in SU5, which are all left-handed, and therefore you have maximal parity violation. And in the end, you see that the long-range forces, U1 and SU3, respect parity. Why is it? Well, I don't see any real explanation. If you want to go to give some mathematical, so quote unquote, argument, you would observe that SU5 has anomalies which are compensated between the 10 and the 5 bar. And as Stoft indicated, when you break down your theory, you should keep track of the anomalies. And if the anomalies are 0, you must end up with 0 anomalies. Well, you have a U1. The simplest way to have 0 anomaly in a U1 is to have a vector-like theory. And you have an SU3. And in SU3, you end up actually with simple, we start 10 and 5 bar, you end up with 3 and 3 bars. So basically, saying you don't have anomalies and looking at the representations you have, you see that you end up with a vector like SU3. So this is not a very good argument, but I think it's maybe one question we should keep asking ourselves, because gravity, of course, also is parity conserving. Okay, actually, you might phrase it differently. When you break the theory, you see that all unbroken or all subgroups lead to parity conservation, except for SU2, which is not susceptible to anomalies because it's pseudo-real. So that's the only one which had a chance of not respecting parity, and it doesn't respect it. Okay, so too bad for parity. This is not a way to characterize really the weak interactions. This is things which happen for all gauge interactions, parity breaking. The next thing is CP. Okay, CP is something which is usually a scary issue for people who don't make a living out of it. But okay, CP is for me a very important thing, and this is why I essentially have focused on CP. If you look, CP for gauge theory, CP in 3+1 dimension is the characteristic symmetry of gauge interactions. And by this I mean pure gauge. That means no mass no scalars, no mass term, and therefore no anomalies, because the anomaly can always be rotated away. Well, this is easy to see. Okay, first of all, a quick definition of CP for those who are not in the field. This is a late KDK experiment, CP-Lear. It was many years ago, but it was one of the latest setups. You have a beam coming across the screen, collides in the middle, and here it produces, I think it's an anti-K0, which is produced here. You know it is an anti-K0 because you identify here a K, was it a K minus, which is produced in the same time. So you know this is an anti-K0. And it propagates, and you don't see it because it's neutral. Then it decays. And it decays and gives you an E+. And if you work it out, you see that if something produces an E+ and has the mass of a K0, this is a K0 and not an anti-K0. So this is a very pedagogical experiment, if you wish. This is the way B physics is done, but that's easier to see here in K physics. You have this probability. Unfortunately, this doesn't show up well on the black. I'm sorry, it was showing right on my screen. What you can compute the probability that the K0 bar here moves into a K0. Then you can do many such experiments, and you can compare the probability that the K0 bar goes into a K0 to the probability that the K0 goes into a K0 bar. Now, the two probabilities are related by time reversal or by CP. CP of K0 is K0 bar. So the two probabilities are related by CP or T, and they should be equal if CP or T is observed. And in fact, you find that there is a 0.6% difference in the probabilities, with the K0 bar going to K0 being more likely than the K0 to the K0 bar. Okay, this was a small parenthesis to remind you what is going on. Now, why is it a characteristic of gauge theories? This is a heuristic slide. We have to go into much more detail. Basically, if you take a gauge interaction here, and you take the Hermitian conjugate, which is always in the Lagrangian, Well, you get this. Instead of having an outgoing electron, you have an incoming electron, and vice versa for the neutrino. Now you remember that a line like this, or a left-handed electron moving to the right, is equivalent to a right-handed electron, positron moving to the left. So you rewrite this one in those terms, and you see that these two amplitudes here are CP conjugate. You have to go into more details if you want to be completely correct. They are related by G and G star, and we have a unitary gauge theory, so G is a real constant here. In this, you can change basis and make it complex, but here it is real, and therefore CP is automatic. And this is true in 3 dimensions. 3 + 1 dimensions. Okay. So how do we, in this theory, account for CP violation? Because we have CP violation in the case system. We had it in the case system. We have seen it in the B system. And we know that we need CP violation if we want to account for the baryon number of the universe. Of course, this is a bit more of a conjecture, but we have observed a non-zero baryon number of the universe, and we are part of it. OK, so you cannot do it with the gauge forces in 3 + 1 dimensions. And that's the moment where you introduce the feeble force. And indeed, the feeble force, this is the coupling of the scalar boson. The scalar boson, sorry, which gives you, first of all, I present it as a joker. You'll see why later. Because, you know, it's really a joker. It's a little bit like cheating. When you cannot do something in a card game, you can always shuffle in a joker as a replacement. And here, what you get is indeed a very small coupling. This is the gauge coupling, and you see, for example, for the electron, you get something like 10 to the -5, 10 to the -6. And this time, we indeed have a weak interaction, and to avoid confusion with the old weak interaction, which was not weak, I will call it a feeble interaction. OK, what does that mean? Well, when I get here, all those lambda coefficients are arbitrary, and there is no reason they should be real. And so, of course, there is much more needed. Depends on the number of families you have. But basically, when you do this complex conjugate diagram, this CP conjugation, you get lambda and lambda star, and lambda star has no reason to be equal to lambda. Now, you can rotate many phases away. If you are in the standard model, you need 3 families, 3 generations. This is the Kobayashi-Maskawa generalization of the Cabibbo matrix. But if you work in a left-right symmetric model, for example, you have already CP violation with 1 family. But the fact that you are in a standard model or in left-right model tells you of how many phases you can brush under the carpet. But the phases are not there because of the gauge interactions. They are there because of the feeble interaction. OK, this is the comment about the joker. Now, what is remarkable is that, well, of course, CP violation was known from 64, I think. This was an interesting year, 64, for several things, because in the same way, the same year, we found 2 indications of the presence of a scalar boson. One was the Brout-Englert-Higgs mechanism, and the other one was CP violation, which for me is kind of the proof of the existence of some form of scalar bosons. OK, now, of course, when the scalar bosons were introduced, first of all, they were not introduced in the context of weak interactions. It was much more generic. And they were introduced to give mass to the gauge bosons. And at that time, for example, if you had strong interactions, you could think that the fermions, the quarks, would get a mass just by hand and be vector-like and not have CP violation in that sector. You could think of that. Later on, when we knew that the standard model was chiral, And to know that it was chiral, it had to be determined quark by quark at the lab and other machines. For each quark, we had to check that the left-handed and right-handed couplings were different. Later on, it turned out that we needed also the scalar boson to give the masses to the quarks and to the leptons. And this led, of course, when you have the gauge interactions, we have three families which only speak only speak within the family. Everything stays within the family, U1, U2, U3. They speak only to the up only speaks with down partner, and it's only through the interaction of the feeble interaction of the scalar boson that those get masses. The masses are not diagonal in that basis, and you move to the mass basis. Why? Because the mass basis is essentially how much energy you need, and your accelerator costs a certain number of Swiss francs. So for a certain number of Swiss francs, you can afford this generation or this generation or this generation. And that's why you take the mass basis in some way, and you get those interactions. Now, I'm not sure whether I have not put this here. I will make a comment later. You see that the interactions which are still gauge mediated in this new basis, they go almost in all directions, but they never go horizontally. These are called flavor-changing neutral currents, and they are very strongly suppressed. And it's, again, a 10 to the minus 10 suppression, which was a big success of the standard model and, for example, of the GIM mechanism. OK. Now, this is just one comment. The fact that we have a feeble interaction and not the artificially weak interaction is also the explanation why it took so long for accelerators, and actually for CERN in that case, to go from the W and Z just below 100 GeV to the H just above 100 GeV. And it took from 1983 to 2012, that's about 30 years. Well, it's not this difference in energy which makes the difference. It's, of course, the difference in the couplings. And this is why I think that LHC, even if they feel a bit wimpish about it, could be, I was teasing Peter Jenny yesterday. He said he was feeling a bit wimpish of dealing with feeble interactions, but you need to be a strong man to deal, a strong person, sorry, to deal with feeble interactions. OK. Now, the next question, of course, is nobody likes the scalars. Well, they might be there for supersymmetry, but that's a different story. But even in supersymmetry, the scalars with greater symmetry are introduced by hand in a way. You get partners of the usual fermions, but those are not the ones you use for the Brout-Englert-Higgs mechanism. So supersymmetry doesn't change much, except you have fundamental scalars in supersymmetry anyway. And the one reason you don't like them is because they introduce so many arbitrary parameters. All the masses, all the coupling, all the mixing angles, and so on. And you can just fit it. Actually, if you remember, nobody made sense of that. Actually, there are lots of people who have done kind of numerology, discrete symmetries, A4 permutation, you name it, to try to predict the charged lepton masses. And the only one which, well, of course, one was predicted by experimental constraint. That was the charm, but that was not one of those numerology calculations. This was just an experimental measurement, in a way, the prediction of the charm mass. The other ones, nobody ever made a prediction. People for the top quark, if I remember, people stopped making predictions at 35 GeVs, and it was found much later at 170. They had foreseen any mass between 5 and 35 GeV in between. So they were so successful in not predicting the quark masses that now they are doing the same game for lepton masses. We'll see a little bit more about it for the moment. OK. Now, there are various ways. One thing would be that those scalars would be composite. Well, I fell in that soup when I was a kid, because this is what we did with François at the time looking for dynamical symmetry breaking. And that's, of course, a very nice hypothesis. It has been retaken, as John mentioned, as in the name of Technicolor. It reappears in various other names. What is clear is that the H particle, which you see now, is a very narrow state. So if it is a bound state, it's a very tightly bound state, and it probably means a Goldstone boson of a symmetry which is broken at a rather high mass. Now, I will come back to these possibilities. No, so I'll follow a few strategies here. Let's stay in 3+1 dimensions for the moment. My problem is CP violation. And the question is, could we get CP violation in 3+1 dimensions from a CP invariant Lagrangian? Let's imagine that I get the pseudo-Goldstone bosons, I get the scalars as bound states from a fundamental gauge theory. The fundamental gauge theory is CP invariant. I expect the potential will be CP invariant. And then I need to see if I can do a spontaneous breaking. That means that I can get various scalars to have various phases, so I generate the breaking. And this would be another spontaneous breaking of CP, but this time of CP. Now, this has been studied several times. I think T.D. Lee already had some models on that. I just went back to a paper by Gustavo Branco. For example, if you instead insist on having no problem with flavor-changing neutral currents, you can do it in the standard model, SU2 cross U1, at the cost of introducing 3 doublets. And that means that you get 3 vevs, which essentially form a triangle. You need 3 to get a triangle in complex space, a non-vanishing triangle. So that's a fairly simple argument. And it works. But it works so well that it gives you some kind of super weak CP violation. That means that the CKM matrix is real. And therefore, you don't predict anything significant in terms of direct CP violation. And it contradicts experiment. And it also contradicts K2 pi L3 in passing. So this model was predictive and therefore excluded. It might be interesting to go further and release those constraints. And there is also a paper here also with Branco, which introduces more fermions to achieve the same goal. So I think this is one direction of research which could be reactivated to see whether CP violation is spontaneous or not, which would be an indirect way to get at the compositeness of the scalars. Sorry. OK, this was a comment about flavor-changing neutral currents, but since I already made it, I will just skip it. This is just to show you that, indeed, the measurements of CP violation here, they correspond very well with the CP violation being in this Kabibo-Kobayashi-Maskawa matrix. I will come back to it, and you have an angle beta here, which will play a role a bit later. I don't want to go into details. Now, there is another model which is very nice for this, and especially if you want to compute the theta parameter, the left-right model is very nice because you can have it impose the CP parity or the T parity on the left-right model, and then you can compute theta because theta is 0 at tree level, and you can compute it as a finite number. In general, it turns out to be helpful, but OK. In this left-right model, you have what is called a bi-doublet. So think of this as one doublet of scalar fields and a second doublet of scalar fields. It's just like the 2 scalar fields which appear in supersymmetry, the one with hypercharge 1 and the one with hypercharge -1. They get vacuum expectation values, which are different in general, and you can get a phase between the two. So again, you have a phase, you will get CP violation, although the rest of the Lagrangian is real. And it's very nice, and it works very nicely for the K system. It even gives you nice epsilon prime over epsilon. This is pretty cute. We did calculations on that quite some time ago. We did calculations of that, and we showed that in this minimal version of the model, neglecting, well, as you may see, the half-flavor changing neutral currents in this theory, to control them, you assume that the scalars which change the flavor current are sufficiently heavy, and in that limit, we should put a strict bound on one parameter assigned to beta, which is the CP violation in the B system. We put that parameter shortly before it was measured. The first measurement came with this value. And then the measurements were improved, and they got a completely different value, which means that this spontaneous CP violation left-right is excluded. Is excluded. Of course, you can go further, try to put more scalars, take into account the flavor change in neutral current scalars and so on. But it becomes really, I think it becomes really a messy game because you have too many parameters. So this should be revisited when we get to see a W right. For example, as soon as you have found a W right at the LHC, it would be very nice. By the way, I don't mention it in those slides, but if and when you discover a W right at the LHC or at any future collider, you basically disprove the basic approach to leptogenesis because you get too much dilution and leptogenesis fails. It's probably one of the few ways to disprove leptogenesis, very few ways. Okay, now I was careful to say that CP is a property. How much time do you have? Do I have? Quarter, no, okay. That's more than enough. Okay. So another question is whether we can get CP violation from extra dimensions. I was careful to say that CP was the symmetry of gauge interactions in 3+1 dimensions. But it's not true when you change dimensions. In 5+1, for instance, the symmetry of the gauge interactions is C, it's charge conjugation. It's not CP. And whether you have CP or not depends on your choice. You have, again, semi-spinors in a way. Well, if you make a vector-like theory in 6D, you get CP. If you make not a vector-like theory, you don't get CP. The reduction from 5 to 4 or 6 to 4 will involve changing dimensional reduction, may bring some of the CP violation from the extra dimensions to the 3+1 dimensions. But it's not a trivial thing. First of all, when you compactify 5+1 to get 3+1, you indeed, and you do simply your mechanism, you indeed, on the dimensionally reduced theory, you indeed get nominally the CP invariance for the gauge part. For the 4 gauge bosons, A1, A2, A3, and A0, you get the CP invariance. But there are 2 more gauge bosons. Now, what is happening? Okay, this is just one example of the wastefulness of dimensional reduction. In 5D, you have something like, which is seen for 4D, is a vector-like approach, and you reduce to a purely chiral multiplet. In 6D, you get 2 such multiplets, and you end up still with a chiral state. Okay, this is, you have to work out your compactification to get that. You may see more details in a few next slides. So let me look, for example, at the case of 5D into 4D. If I work with 5D, I have, as I mentioned, the WAs. A is 0, 1, 2, 3. That's the usual ones. And then 4. The gamma 4 matrix here, the gamma 4 matrix, when you look in terms of Dirac matrices, this is I gamma 5. So that means that the 4th component of the W essentially couples like a pseudoscalar when it is seen from 3+1 dimensions. You get a pseudoscalar. That's a good way to be on the way to CP violation, because a pseudoscalar and a scalar are typically a complex mass term. So you're in the right direction. Now, it is not exactly that simple, because saying that W4 would have a VEV is not a gauge invariant statement. And what you need to do is to do a loop integral. For example, imagine you have compactified on a circle. You do a loop integral of W4 d4x. This means the flux going through the loop in 4th dimensions. And this quantity there is then helping to break CP. Well, I'm cheating. I'm cheating because I've put a mass parameter here. And indeed, if you have this mass parameter and the I gamma 5 there, you can build a model. You would need to put an SU2. And we have built a model where you can get an electric dipole moment for a massive fermion, in this case, not from pure gauge and the mass term. And this mass term is cheating. By the way, in 5D, a mass term is parity violating. It may look strange, but it's like that. It's just like that. OK. It's not very pretty. We have more recently with Maxime Libanov and, oh, sorry. This means Simon Mollet. There was some problem with the, well, François is familiar with this question. OK, sorry, Simon Mollet was my last student. We did some study in 6D. And in 6D, the idea is that you get W4 and W5 now, and W4 plays the role of a pseudoscalar, and W5 plays the role of a scalar. So compactifying from 6D to 4D, you can get both the scalar and the pseudoscalar, so you get the complex mass term, starting only from gauge theory. And we worked out an example. You have to do the Ozotani, look at the stability, and so on. The paper is rather involved. You can, as you know, with CP, it's always the only way to know whether you have CP is to compute a CP violating observable. Otherwise, you may always worry that you can hide the phases somewhere. And we worked out you can work the case of one massive fermion. You can get one massive fermion with an electric dipole moment, which is a CP violation. Now, to build that into a flavor model, when you look at the complexity of this thing, is kind of a daunting task. But it's not impossible. It's just a proof of principle. OK. Now, for the last part, I'm just jumping off my favorite horse, which is CP violation. And I'm attacking, in a more naive way, just the multiplication of the coupling constants. As I mentioned, there have been all kinds of attempts to use all kinds of crazy symmetries to restrict the Yukawa couplings, and nothing has ever come with a tested prediction. Lots of postdictions, but no tested prediction. Now, again, extra dimensions can come to the rescue. Well, there is one well-known example, which is 4+1, which is multilocalization. You can call it, if you make a warp metric, you can call it Randall syndrome. Basically, what you do is you take the 5th dimension here, we call it Y. You arrange that for any point in our space. There's a point in our space here. The one fermion is located at some distance in the Y direction. The other fermion, say the left-handed here, the right-handed there, at some other distance. And then the mass is computed with the convolution of the two wave functions with the scalar boson. OK, what do you gain? Well, you gain not much, because basically, whether it's Randall syndrome or something else, yeah, there is an L missing, you don't gain much, because basically that means that you tune your masses by tuning the location in the fourth direction. So this is just a bijection. The gain is that since you are playing with the tails of the Gaussian functions here, you can get very big mass ratios. And so it looks more natural, like in Reynolds syndrome, you know, e to the 10 to the 10 looks like a large number, but e to the 10 to the 15 looks like a large number, but e to the 45, when you only look at the exponent 45, it's argued that it's a small number. So this is basically what you are gaining here. You are gaining sensitivity by playing the tails. Now this is another example which it's a model we have worked on as a toy model, if you wish, but it has some interesting things. It's also relatively heavy. This is work done with, again, Maxim Libanov, Sergei Troitsky, and so on. We start in 6 dimensions. And to get the compactification and the isolation of the chiral modes, which I mentioned, we work with the vortex in the extra 2 dimensions. Here, this is the vortex defined by a scalar field. And for some reason, we choose that the vortex winds 3 times. Why 3 times? Because to each winding number, unit of winding number, we get a massless fermion. So starting from one family in 6 dimensions and putting a winding of 3, we get 3 fermions in 4D. So this resolves the family problem, except you have to put in 3 by hand. OK, this is life. 3 is a number. And the wave functions are actually very predictable. They are typically like you expect with non-zero intercept, non-zero first derivative, non-zero second derivative, and they each have their different winding numbers here. And when you can compute the masses, actually the winding number serves as a family number, and you get a very predictive. There are many parameters in the theory, but it's extremely rigid. And you get this small, medium, large, because you get the overlap, which is here, very small with the scalar boson, larger and much larger. Of course, here we introduce the scalars by hand. So this is, again, cheating if you wish. If you want to go a bit further, we can introduce more fields using the vortex, and we can introduce the mixing. This is what we get for the quarks. Well, this far it's not terribly interesting, except you get a much more rigid model, and you get family number conservations and predictions that the first observable would be k long into mu bar e, which is 10 to the minus 12 branching ratio, and that puts you a scale around 100 TeV typically. You can cheat a bit and bring it lower so that people at LHC should be looking for mu bar e. And I think they have been, and they forgot to quote our papers, which we had mentioned for many times before. No, I had advocated looking for z prime into mu bar e, but this is a Belgian story. Louvain-la-Neuve was looking into mu bar mu, and Brussels was looking into e bar e, and I couldn't get one to look into mu bar e. Okay, but finally they did. Okay, now the interesting thing is when you write the neutrino matrix, and you insist on getting Majorana neutrinos, which is non-trivial because in 6D there are no such things as Majorana neutrinos. But when you go to 4D, you can get Majorana neutrinos, and you get this anti-diagonal matrix. An anti-diagonal matrix means when you diagonalize it, of course, means you need a large mixing angle in the neutrinos. You get 2 large masses. Don't pay attention to the minus sign for the moment. You get 2 large masses and a small one, which is inverted hierarchy. And the minus sign here means you have something which is called pseudo-Dirac suppression, which is the kind of fine-tuning that people like to put in by hand in some models. And what we get then, that means we get suppression of the neutralized double beta decay, which is at the bottom of the band, which is also the part which is difficult to reach for Gerda, for example. So this is the game. We tried to fit parameters. It's very rigid. We have many parameters, but we couldn't find a fit. except for a θ1 triangle around 9 degrees. This was before it was measured, at the time where everybody was advocating tri-bimaximal mixing and 0 for this value. Okay, I don't insist on the prediction. This was the, go too far. This is the conclusion. Since I'm short of time, I will stop it. And this is why you saw all this vegetation pictures in between, just to refer to the Gardener of Eden.
It's working? Yeah. So I would claim actually we did make one successful prediction for a fermion mass based on a symmetry. Mm-hmm. And that was grand unified SU5. So in the simplest SU5 model, the tau lepton and the bottom quark have the same Yukawa coupling. But then that's renormalized in the same way that psi squared theta w is renormalized. And we actually use that to predict the mass of the bottom quark a few weeks before it was discovered.
Okay, good. It's okay. I didn't remember the timing. Indeed, in the SU5, if you assume only the 5, you get that prediction. And then, since it doesn't work so well for the other fermions, people started putting in the 45. And the moment you put all the possible representations, you lose all predictions. But this is indeed an important point, and this is one of the reasons I think that grand unification is superior to just saying, look at the cancellation of anomalies to fix the coupling constants. Because there is now a vicious circle. We went to grand unification. Then people wanted supersymmetry to stabilize grand unification. I don't agree completely. Then from supersymmetry, they went to string theory. And string theory then wants to come back to SU3 cross SU2 cross U1 without going through the grand unification. So there is something which is bothersome, and grand unification tends to disappear from the curriculum nowadays, which I find regrettable. But indeed, there is this, the mass predictions are the thing which are unique to grand unification.
Okay.
But it was not one of the discrete symmetries of
Right, it's a different type of symmetry.
Yeah, it was essentially grand unification.
Okay, well, I think it's time for us to go and get some food and thank Jean-Marie and Sarah. Yeah.
Oh, sorry, I forgot the provocation at the end. Just to remind that what we are looking at is only tested on the finite range. And for gravity, that means it's tested to a few milli-electron volts. And the problems arise at 10 to the 28 electron volts.